Hello, everyone, and welcome to our DSA series. I'm your host, and today we are diving deep into the whiteboard session on one of the most powerful and versatile tool in our coding interview arsenal, the hash map. If you look at the left side of a board, you see that messy desk of a search problem. Without a hash map, finding data is like rummaging through the mountain of loose papers. It's chaotic and slow. But on the right, we have a filing cabinet. By using hashing and frequency counting, we turn these tedious search problems into an instant lookups. Today, we aren't just counting characters. We are learning how to organize data so the computer can find exactly what it needs in constant time. Make sure to follow, like, and press that notification icon so that you don't miss our subsequent topic in this series. For more DSA and interview prep content, be sure to explore the channel. Let's get to work. The core philosophy of this session is simple. Stop scanning and start looking up. In a typical O of N square, you are like a stressed out librarian running through the aisles. We are asking, is the book here? No. How about here? No. This repetitive looping is the enemy of performance. When we use a hash map, we transition to a card catalog system. Instead of running through the shelves, you go straight to the index. It tells you exactly where the data lives. Row 4, shelf B, done. This moves up from O of n time, which grows with the size of your data, to O of 1 time, which is nearly instantaneous. In an interview, the moment you find yourself comparing elements repeatedly in nested loops, you should be thinking, can I transform this search into a lookup? That thought process is exactly what separates junior developers from senior engineers. Now, let's look at a basic building block, the frequency map. Imagine we have a word hello. To understand this string algorithmically, we want to look we want to know exactly what it is made of. We iterate through the string and drop each character into its own specific bucket. As you can see, H gets 1 tally, E gets 1, L gets 2, and O gets 1. The resulting object? Count H1, E1, L2, O1. This is the DNA of our string. Because we touch every character exactly once, the time complexity is a beautiful O of n, and the space complexity is O of k, where k is the number of unique characters. If you're only dealing with the English alphabet, k is capped at 26, meaning your space is essentially constant. This little map allows us to answer questions about character counts instantly. This is a pro tip for your actual interview. Don't waste time writing boilerplate code. On the left, we see too much ceremony approach. You're manually checking if a character is in the dictionary, then incrementing or initializing. It's noisy, error prone, and slow to type while you are under pressure. Instead, use the industry standard collections.Counter. In one single line, counts equals collection.Counter. Hello, you've done all that work. Not only is it cleaner, but it also signals to your interviewer that you know the Python standard library inside and out. It even gives you powerful methods like most common for free. When you're on the clock, every second and every line of code counts. Show them you know the tool of the tirade and by using the most efficient syntax available. Now let's apply our frequency map to a classic problem, the anagram challenge. How do we know if listen and silent are anagrams? By definition, true strings are anagrams if and only if their frequency maps are identical. If we break listen into buckets, we get one of each letter. If we do the same for silent, we get the exact same distribution. In our code, you can simply compare the two maps. If counter of string 1 is equal to double equals actually counter of string 2, you have a match. This is a much more elegant than trying to sort the string or use nested loops. It gets straight to the heart of the mathematical property of an anagram. It's not about the order, it's about the inventory. If the inventory matches, the strings are anagrams. There's a common debate: should I sort or should I hash? Sorting is safe, it's easy to implement and understand, but as you can see from our little car on the hilly road, sorting is n log n. It is an uphill battle. You have to sort both strings, then compare them. Hashing, represented by the rocket ship, is O of n. It's a straight shot. You do one pass to count the characters and one pass to compare the maps. While O n log n might pass some test cases, if you want to truly impress your interviewer, you go to the linear time O of n solution. Using a hash map shows you are prioritizing performance and understand how to scale your code for massive inputs. Always aim for the rocket ship when a linear path is available. Things get interesting when we move into substrings. Imagine searching for a pattern ABC within a long string S. This is the classic needle in a haystack problem. If we take a magnifying glass and recalculate the character frequencies for every single three-letter window, we end up doing O n times m work. This is the calculator on fire scenario. It's too slow because we are doing redundant work. When we move our window from index 0 to index 1, most of the characters stay the same. Recounting B and C over and over is a waste of CPU cycles. We need a way to move through the string without rebuilding our frequency map from scratch every single time. We need a sliding movement. Enter the sliding window technique. The mantra here is: don't rebuild the house, just open the front door and close the back door. When we slide our window one position to the right, we do exactly two things. We look at the character exiting the window on the left and decrement its count in our hash map. Then we look at the new character entering in the window on the right and increment its count. This update don't rebuild strategy is the secret to high performance string processing. By only updating the edges, we keep our operation at a constant per step cost, which is the key to achieving that coveted linear time complexity. Let's trace the logical flow of this update. We start by initializing your pattern counter and our first window counter. Then we enter the slide phase. We move the index. The update is simple. Window of outgoing minus equals 1 and window of incoming plus equals 1. There's one vital cleanup step. If a character's count drops to 0, we delete that key from the map. This keeps our map clean so we can simply check if window equals pattern. Because these updates and map comparison for a very small fixed size problem are constant time, and the overall complexity of searching the entire string drops from O n times m to O of n. We have turned a very heavy multiplication problem into a simple addition problem. But what if the strings are absolutely massive, like a DNA sequences? In genomic research, you must be looking for the duplicate sequences that are thousands of base pairs long. Even with a sliding window, comparing two massive frequency maps or substring character by character can still take O of k time, where k is the window length. When k is large, our performance starts to dip again. We need a shortcut. We need a way to represent a long string of text, not as a collection of characters, but as a single unique integer. We, if we can turn ACTG into, let's say, 5829, comparing two sequences become as fast as comparing two numbers. This is where we move from a basic hashing into the world of rolling hashes. Think of a rolling hash as a meat grinder for data. You put in a string like ABC and it cracks out a single number like 294. This is done using a polynomial rolling hash function. The math involves here treating the string as a number in a specific base, usually a prime number like 31. We multiply each character by a power of that prime and sum them up, taking the result modulo, a very large prime number, to avoid overflow and reduce collisions. The formula looks complex, but the idea is simple. Every unique string gets a fingerprint number. This fingerprint is what we'll use to identify matches in record time. Why do we call it rolling? Because of how we update the number. Look at this conveyor belt. We have a sequence of 4 to 7. When the window shifts from 271, we don't recalculate the whole math equation. Instead, first, we subtract the leading term, which is 4 in this particular case. Second, we shift the powers by multiplying or dividing by our prime base. Third, we add the new trailing term, which is 1 in this case. This update happens in O of 1 time. This is a massive breakthrough. Comparing two huge strings that are thousands of characters long now becomes as fast as comparing two integers. Whether your window is 10 characters or 10,000 or 10 million, the update cost is same. This is the logic behind the Rabin-Karp algorithm. Now we have to talk about the gotcha. Hash collisions. Sometimes two different strings, like the cat and the dog, might accidentally produce the same hash value, say 123. If we just trust the number, our algorithm will give a false positive match. There are two primary fixes. First, double hashing. Use two different set of primes to generate two different hashes for every string. The probability of both hashes colliding simultaneously is astronomically low. Second, verification. If the hashes match, do a quick manual string check to be 100% sure. Since collisions are rare, this manual check almost never happens. So our average time stays super fast. Being aware of collision is what makes our solution production ready. Here is a pattern, cheat sheet for the interview. If you have a pure counting problem, like ransom note or first unique character, your tool is a counter. If you need to group things, like in the case of group anagrams, use a tuple of counts as your map key. If you see movement like min window substring or find all anagrams, use a sliding window plus the counter. And for the big data problems like massive substring, like in the case of DNA repeats, pull out the rolling hash. Don't memorize the problem, memorize these mappings. When you see a specific problem type, your brain should automatically reach for the corresponding tool in the cabinet. To wrap up, master the map and you'll master the interviews. Always ask yourself, can I trade a little bit of space, O of k, for a lot of time? If the answer is yes, build a hash map. We have moved from a slow O of n cube loops through the logic blue path to efficient ONL frequency map and finally to the star of the show, rolling hashes with O of 1 updates. This journey from messy searching to instant lookup is the heart of algorithmic optimization. Thanks for watching. We've got plenty more coming in this series. Comment below and let me know which topic you'd like to see on the whiteboard next. See you in the next session.